Section 6.7. Binary Arithmetic. The table covers all 7 operators. Star, multiplication, or repetition when you multiply an integer by a sequence. @ matrix multiplication. No built-in type implements this. It's for NumPy and similar. / division always returns a float. / floor division returns an integer for integer operands. % modulo result sign matches the second operand. Plus addition or concatenation for same type sequences. Minus subtraction numeric only. The info box adds a Python 3.1 detail. If only one operand is complex, the other is converted to float for multiplication, addition, and subtraction. Binary arithmetic in action. Line 1. 7/2 is 3.5. True division always gives a float. Line 2. 7 /2 is 3. Floor division. Line 3. 7% 2 is 1. Modulo. Line 4. 7% -2 is -1. Sign follows the divisor, the right operand. Line 6. 3 * ab gives ababab. Integer times sequence gives repetition. Line 8. 10 + 3 is 13. Line 9. 10 - 3 is 7. 2 key rules. / always gives a float. Use / when you need an integer result. And the % rule. The result takes the sign of the right operand, not the left. 7% -2 is -1, not +1. Section 6.8 and 6.9. Shift and bitwise operators. Left column shows the shift grammar. A shift expression is an arithmetic expression, or a shift expression shifted left or right by an arithmetic expression. Left shift, double less than, shifts bits left, equivalent to multiplying by 2 to the power of n. Right shift, double greater than, shifts bits right, equivalent to floor division by 2 to the power of n. Both accept integers only. Right column covers bitwise, and single ampersand sets a bit only if both operands have it. XOR, caret, sets a bit if exactly one operand has it. Or pipe, sets a bit if either operand has it. Bitwise operations on x equals 0b and term 10. That's 10 in binary. Line 3. X left shift. 1 gives 20. Multiply by 2. Line 4. X right shift. 1 gives 5. Floor divide by 2. Line 6. X and 0b 100. We keep only bits set in both. 10, 10 and 1100 gives 1000, which is 8. Line 7. X XOR 0b 100. We set bits that are in exactly one operand. 10, 10 XOR 1100 gives 0110, which is 6. Line 8. XOR 0b 001. We set any bit in either. 10, 10 or 0101 gives 1111, which is 15. 2 key rules. Shifts are fast math. Left shift by n multiplies by 2 to the n, right shift divides by 2 to the n, integers only. And keeps bits set in both. OR keeps bits set in either. XOR keeps bits set in exactly one. Section 6.10. Comparisons. Value comparisons, membership tests, and identity tests. Python's comparison operators are chainable. You can write 1 less than x less than 10, and it works exactly as you'd expect mathematically. We'll look at how each comparison type works under the hood. Lines 1 and 2 show the grammar. Comparison operators include less than, greater than, double equals, greater than or equal, less than or equal, not equal, is not in, and not in. 2 key properties. Same priority. All comparison operations have the same priority, lower than arithmetic, shifting, or bitwise ops. And chaining, comparisons can be chained. X less than y less than or equal z is equivalent to x less than y and y less than or equal z, with y evaluated only once. That's the important part. Y is only evaluated once, not twice. Comparisons in action. Line 1, 1 less than 2 is true. Line 2, 2 double equals 2.0 is true. Numeric comparison across types. Line 3, A less than B is true. Lexicographic by Unicode code point. Line 6, x equals 5. Line 7, 1 less than x less than 10 is true. Chained comparison, same as 1 less than x and x less than 10, but x is only evaluated once. Line 8, the equivalent using AND, same result. 2 key rules. Chaining saves a variable and evaluates the middle operand only once. It's not 1 less than x less than 10, which would compare a bool to 10. And double equals tests value equality. Is tests identity. Use double equals for values. Is only for none, true and false. Value comparisons in detail. 4 boxes. Numbers. Compared mathematically across types. Complex numbers don't support order comparison. Nayan is not equal to anything including itself. Strings and bytes. Compared lexicographically by Unicode code point. Strings and bytes cannot be directly compared with each other. Sequences. Compared element by element within the same type. The shorter sequence is ordered first if all elements match. Sets. The less than and greater than operators mean subset and superset tests, not a total ordering, so you can't sort a list of sets. Value comparisons in practice. Line 2, 1, double equals 1.0 is true. Cross-type numeric comparison. Line 3, float. Nayan double equals float nayan is false. Nayan is never equal to itself. Use math.isnan to test for nayan. Line 6, ABC less than ABD is true. Lexicographic, they differ at the third character. Line 7, Z less than A is true. Uppercase letters have lower Unicode code points than lowercase. Line 10, list 1, 2 less than list 1, 3 is true. Element by element. First elements match, second differs. Line 11, list 1, 2 less than list 1, 2, 0 is true. The shorter list loses when all its elements match. Line 14, set 1, 2 less than set 1, 2, 3 is true. Proper subset. Line 15, set 1, 2 less than set 1, 2 is false. Not a proper subset. They're equal. 2 key rules. Nan is never equal to itself. Use math.isnan. And for sets, less than means proper subset. It's not a total ordering. If you're implementing comparison methods on a custom class, there are 4 rules to follow to keep things consistent. Reflexive. If x is y, then x equals y must be true. Symmetric. If x equals y, then y equals x. Transitive. If x is greater than y, and y is greater than z, then x is greater than z. And hash consistent. Equal objects must have the same hash value or be marked unhashable by setting dunder hash to none. The warning box is important. Python does not enforce these rules. NaN values are a known exception. They violate reflexivity. The functools.totalOrdering decorator can help. Define dunder EQ and one ordering method, and it fills in the rest. Section 610.2. Membership tests. The in and not in operators test for membership. 3 arrow bullets. Strings and bytes. X in Y is true if X is a substring of Y. Custom classes. Python tries dunder contains first, then dunder iter, then dunder getitem, in that order. And the empty string gotcha. The empty string is always a substring of any string, so empty string in ABC is true. Not in is just the logical negation. It's not a separate dunder method. Membership tests in action. Line 2. Cat in a list of animals is true. Linear search. Line 3. Pi in Python is true. Substring check. Line 4. Empty string in anything is true. The empty string is always a substring. Line 7. 3 in a set is true. 01. Hash lookup. Line 8. Key in a dist is true. Tests keys, not values. Line 11. 99, not in range 10, is true. 2 key rules. In on dix checks keys, not values. Use x in d dot values to test values. And the empty string gotcha. The empty string is a substring of every string, so that check always returns true. Section 6.10.3. Identity comparisons. Left column. Is. X is y is true if and only if x and y are the same object, same ID. Right column. Is not. Yields the inverse truth value of is. The info box cites PP8. Use is and is not only for singletons like none. Use double equals for value equality. Is cannot be overridden. It always checks object identity, regardless of any dunder EQ implementation. Identity comparisons in practice. Line 1, x equals none. Line 2, x is none is true. Correct pattern for none checks. Line 4, p equals list 1, 2. Line 5, q equals list 1, 2. Same value, different objects. Line 6, r equals p. Just another name for the same object, an alias. Line 7, p is q is false. Different objects in memory. Line 8, p is r is true. Same object. 2 key rules. Is checks identity. Same object in memory, not value equality. Never use is to compare integers or strings. And PCEP 8 says, use is and is not only with none, true, and false, never with arbitrary values. Section 6.11. Boolean operations. Lines 1 through 3 show the grammar, or test and test, not test. 4 boxes. Falsy values, false, none, numeric 0, empty strings and containers. Short circuit and returns the first falsy value or the last value if all are truthy. Short circuit or returns the first truthy value or the last value if all are falsy. And not always returns a Boolean, regardless of argument type. That last point is the key difference. And or return one of their operands, which might not be a bool. Not always gives you true or false. Boolean operations in action. Line 1, 0 or hello. 0 is falsy, so we evaluate the right side and return hello. Line 2, hi or bye. Hi is truthy, short circuit, return hi. Line 3, empty list or empty dict. Both falsy, return the last value, the empty dict. Line 5, 1 and 2. 1 is truthy, so we evaluate and return 2. Line 6, 0 and 2. 0 is falsy, short circuit, return 0. Line 8, not 0 is true. Line 9, not ABC is false. 2 key rules. And or don't return true or false. They return one of their operands. Use bool if you need a strict Boolean, and not is the exception. It always returns true or false, regardless of the operand type. Section 6 to 12. Assignment expressions. The walrus operator. Colon equals. Line 1 shows the grammar, an optional identifier colon, equals followed by an expression. It assigns a value to a name and returns that value in a single expression. Added in Python 3.8 via PCEP 572. 2 practical examples. Left column, regex match. If m colon equals pattern.search data, then do something m. We assign and test in one step. No need to call search twice. Right column, file chunking. While chunk colon equals file.read 9000, process chunk. We read and test in the while condition, clean and efficient. Walrus operator in practice. Line 1, data is a list of 6 numbers. Line 4, if parent n colon equals len, data, parent greater than 4. This assigns 6 to n and tests it in one step. Line 5, inside the if body, n is already available. We print long list 6 items. Line 8, nums equals iter data. Line 9, while parent val colon equals next nums, none, parent is not none. We call next, assign the result to val, and test it in the condition. Line 10, print val gives each element in turn, 1, 3, 7, 2, 9, 4. 2 key rules. Walrus has very low precedence. Always wrap it in parentheses when used inside a larger expression like if or while. And PCEP 572 advises using walrus only when it genuinely reduces repetition, not as a general replacement for regular assignment. Section 6.13. Conditional expressions, the ternary operator. Line 1 shows the grammar. An or test, optionally followed by if, another or test, else, an expression. 2 boxes. Syntax. X if C else Y. C is evaluated first. If truthy, X is evaluated and returned. If falsy, Y is evaluated and returned. The other branch is never evaluated. Reference. See PCEP 308 for the design rationale. The key thing, it's an expression, not a statement, so it can appear anywhere a value is valid, inside a list comprehension, an F string, a function argument, anywhere. Ternary operator in action. Line 1, age equals 20. Line 2, status equals adult, if age is at least 18 else minor. Line 3, print gives adult. Line 6, x equals 5. Line 7, label is pos if x is greater than 0, else 0 if x equals 0, else neg. Nested ternary. Line 8, print gives pos. Two key rules. C is evaluated first, and only the chosen branch is evaluated. The other is skipped entirely. And keep it simple. Nested ternaries are legal, but hard to read. If you need more than one level, use a regular if, elif, else block instead. Section 6.14. Lambda expressions. Line 1 shows the grammar. The keyword lambda, an optional parameter list, a colon, then a single expression, creates an anonymous function. The two columns show the equivalence. Left, lambda x, y colon x plus y. Right, the equivalent def, lambda, name takes x and y, returns x plus y. They're identical in behavior. The warning box. Lambda functions cannot contain statements or annotations, no assignments, no if statements, no return keyword, just a single expression. If you need more than that, use a regular def. Lambdas in practice. Line 1, double equals lambda x colon x times 2. Line 2, double 5 gives 10. Line 4, add equals lambda x comma e colon x plus y. Line 5, add 3, 4, gives 7. Line 8, pairs is a list of tuples. Line 9, pairs dot sort with key equals lambda p colon p square bracket. 1. We sort by the second element of each tuple. Line 10, print gives the sorted list. 2, A, 1, B, 3, C. Two key rules. A lambda body is a single expression. No statements, no assignments, no return keyword. Use def for anything more complex. And lambdas shine as short throwaway functions passed to sorted, map, or filter, not as named replacements for def. Section 6.15. Expression lists. Line 1 shows the grammar. One or more expressions separated by commas, with an optional trailing comma. 3 boxes. Tuple creation. An expression list with at least one comma, outside a list or set display, yields a tuple. Trailing comma, required only for a one-item tuple, 42 comma. Empty tuple is just empty parens. And iterable unpacking with star expands an iterable into items at the unpacking site. Supported since Python 3.5 via PEP 448. Since Python 3.11, any item in the list may be starred. Expression lists in action. Line 2, t equals 1, 2, 3. No parens. Line 3, print gives the tuple. 1, 2, 3. Line 4, type confirms tuple. Line 7, 1 equals 42 comma. The trailing comma makes it a tuple. Line 8, print gives 42. Line 11, A equals list. 1, 2. Line 12, B equals list 3, 4. Line 13, print star A comma star B inside a list. The star operator unpacks both lists in line, giving us 1, 2, 3, 4. Two key rules. It's the comma, not the parentheses, that creates a tuple. 42 is just 42, but 42 comma is a one-element tuple. And the star operator expands any iterable inline. Since Python 3.5, you can use multiple star unpacks in a single expression. Section 6.16. Evaluation order. Python evaluates expressions left to right. In assignments, the right-hand side is evaluated before the left-hand side. The code block shows 6 patterns. Line 1, a comma-separated expression list. XBR1, XBR2, XBR3, X before. Evaluated left to right. Line 2, same thing in parens. Line 3, a dicted display. XBR1 colon XBR2, XBR3 colon XBR4. Key before value, left to right. Line 4, an arithmetic expression with parens. Innermost first, then left to right. Line 5, a function call. The callable is evaluated first, then arguments left to right, then star args, then double star args. Line 6. An assignment. The right side is fully evaluated before any target on the left is bound. The info box confirms sub-expressions are evaluated in the order of their numeric suffixes. Evaluation order in action. Line 1, I equals 0. Line 2, def nxt. Line 3, global I, increment it, return it. All on one line. Line 6, print nxt, nxt, nxt. Arguments are evaluated left to right, so we get 1, 2, 3 in order. Line 9, A equals 10, B equals 20. Line 10, a comma B equals B, comma A. The right side evaluates to the tuple, 20, 10, first, then it's unpacked into A and B. Line 11, print A, B gives 20, 10. Clean swap with no temp variable. 2 key rules, left to right, always. Arguments, dict keys and values, and operands are all evaluated left to right, so side effects happen in that order. And in assignments, the entire right-hand side is evaluated before any target on the left is bound. That's what enables the classic A, B equals B, a swap. Section 6.17. Operator precedence. This is the full table from highest to lowest binding. At the top, parenthesized expressions, list displays, dist and set displays, then subscriptions, calls, and attribute references, the primaries, then await, then double star, exponentiation, then unary, positive, negative, and tilde, then the multiplicative operators, star, @ sign, slash, double slash, %, then additive, plus and minus, then shifts, double less than and double greater than, then bitwise and, single ampersand, then bitwise XOR, caret, then bitwise OR, pipe, then all the comparisons, membership, and identity tests at the same level, then not, then and, then or, and at the very bottom, walrus. When in doubt, use parentheses. Arithmetic precedence in action. Line 2, -2 double star 2 is -4. Double star binds tighter than unary minus, so it's -2 squared, not -2 squared. Line 3, parent -2, parent double star, 2 is 4. Parents override. Line 6, 2 plus 3 times 4 is 14. Multiplication before addition. Line 7, parent 2 plus 3, parent times 4 is 20. Parents force addition first. Line 10, tilde 1 left shift, 2 is -8. Tilde binds tighter than shift, so it's tilde 1, left shifted by 2. Tilde 1 is -2, then -2, left shifted by 2 is -8. 2 key rules. Double star is right to left. 2 double star, 3 double star, 2 equals 2 to the 9th, which is 512, not 8 squared. And unary operators bind before binary operators, but less tightly than double star. When in doubt, add parentheses. Boolean and comparison precedence. Line 2, 1 plus 1 double equals 2 and 3 greater than 1. Comparisons bind tighter than and. So this is 1 plus 1, 2, and 3, 1, which is true, and true, which is true. Line 3, not 3 greater than 1. Comparison first, 3 greater than 1 is true, then not true is false. Line 4, not 3 greater than 10. 3 greater than 10 is false, not false is true. Line 7, true or false and false. And binds tighter than or. So this is true or false and false, which is true or false, which is true. Line 8, parent. True or false parent and false. Parents change it. True or false is true, then true and false is false. Line 11, x equals a list. Line 12, 2 in x and x is not none. Both in and is not are at the comparison level, which binds tighter than and. So this is 2 in x, and x is not none, which is true and true, which is true. 2 key rules. Not binds tightest, then and, then or. And all comparison operators bind more tightly than not, and or. Bitwise precedence, and binds tighter than XOR, which binds tighter than OR. Line 2, 0B100 pipe, 0B010, ampersand, 0B0110. And first, 0B010 and 0B010 is 0B010. Then OR with 0B1100 gives 0B1110, which is 14. Line 3, 0B010, ampersand, 0B1100, caret, 0B0011. And first, 0B010 and 0B1100 is 0B1000. Then XOR with 0B0011 gives 0B1011, which is 11. Line 6, 1 left shift 3, ampersand 0B1111. Shift before bitwise, 1 left shifted by 3 is 8, then 8, and 0B1111 is 8. Line 7, 1 left shift paren, 3, ampersand 0B1111 paren. Parens change the order. 3 and 0B1111 is 3, then 1 left shifted by 3 is still 8. Same result here, but not always. Line 10, 2 plus 3 left shift, 1 double equals 10. Arithmetic first. 2 plus 3 is 5, then shift. 5 left, shifted by 1 is 10, then comparison. 10 double equals 10 is true. 2 key rules. Bitwise order is and tightest, then XOR, then OR. Mirrors, and, XOR, or logic gates. And shifts sit between arithmetic and bitwise in the precedence table. Subscriptions and calls bind tighter than any operator. Line 1. Data equals a list of 10, 20, 30. Line 4. Data square bracket. 1 plus data square bracket. 2. Subscriptions happen first. 20 plus 30 is 50. Line 5. Len data, double star. 2. The call happens first. Len gives 3, then 3 squared is 9. Line 6. Negative len data. The call happens first. Len gives 3, then negative 3. Line 10. Text equals hello. Line 10. Text dot upper plus. Attribute reference first, then call, then concatenation. Gives hello. Line 11. Len text dot upper greater than 3. Attribute ref call, then comparison. Gives true. 2 key rules. Calls, subscriptions, and attribute references are primaries. They always bind first, before any operator including double star and unary minus. And you can chain them freely. Text dot upper, square bracket 0 is valid, left to right at the same highest precedence level. Final challenge. Predict the output before running. Line 2. 2 plus 3 times 4 minus 1. Multiplication first. 2 plus 12 minus 1 is 13. Line 3. 2 double star 3 double star 2. Right to left, 3 squared is 9. 2 to the 9th is 512. Line 4. Not 1 plus 1 double equals 3. Addition first. 1 plus 1 is 2. 2 double equals 3 is false. Not false is true. Line 5. And first, 4 and 6 is 4, then 4, or 1 is 5. Line 6, comparisons first, true and true or false. And before or, true and true is true, then true or false is true. Line 7, double star first, 3 squared is 9, then floor division, 10 double slash 9 is 1. 2 rules. Work inside out starting with the tightest binding operators. And when you're unsure, add parentheses. If you have to think twice, your readers will too.